In this video, we are going to talk about output capacitor on power supplies, because this is one of the very important components, and Ali is going to explain how we can calculate values of these output capacitors. Correct? This is what we are going to talk about?
Yes, that's correct, Robert. That's what we're going to do.
So why do we need this output capacitor on power supplies?
Okay, so predominantly there are two reasons, right? One is that we are trying to reduce the amount of dip on the output voltage. Let's say if the user comes and gives it a big load a step, we don't want the output voltage to dip too much before the control loop kicks in and tries to compensate. So that will be your undershoot requirements. And the second reason is a ripple. The inductor current has got a lot of ripple on it in the topologies where the inductor is directly feeding the output capacitor, for example, like a buck converter. This ripple needs to be reduced. And of course, the job of the capacitor is to reduce this ripple in addition to helping us with our undershoot.
Mm-hmm. So we are basically going to talk about switching power supplies, because there is difference between linear regulators and switching power supplies,
Yes.
Correct?
Yes,
Okay.
yes. For a linear power supply, you still need some capacitance on the output, but that is a completely different story.
Mm-hmm. And I think mostly many people use these switching power supplies, so it's very important to actually learn how to calculate this. So
Yes.
I think we have some measurements, or what is the next step?
Okay, so what I'm going to do is I'm going to show you the inductor current, and then I'm going to give a load step to the power supply, and then show you the dip so that you can see what happens to the output voltage when we give it a load step. Of course, we've got some capacitors on the output and how the capacitor reacts. And then I'm also going to show you the ripple. So you see the inductor current, and then you will see how this ripple that is in the inductor current gets translated into a small amount of ripple voltage. Of course, the more capacitance you have, the smaller the amount of ripple that you have.
Mm-hmm. Okay, so basically we are going to have a look at what the problem is.
Yes. I'm going to just go to the lab on the other side, and I'm going to show you a real power supply and some measurements, and then I'll talk you through it.
Okay, perfect. Let's have a look.
Okay. So here I have got a power supply. This here is there are actually 3 buck converters here. The one that we're going to show is this one, and that is a synchronous buck. We later on will talk about the constant on time in this chat. And underneath is the load. So these switches determine how much load I am giving to this power supply. This is exactly the type of setup that we use in our workshops, and the engineers who come to take the workshop get to play hands-on and experiment like I'm going to show you now. So what I have done is I have taken the inductor current, I've put a loop in it, and the green trace that you see here on the scope.
I don't see the scope.
Please. Yeah, we forgot that, didn't we? So let me just quickly put that on. There we go. Right.
Okay.
Jump to start from the beginning.
No. That's fine.
So here the yellow trace is the gate of the MOSFET of my power supply. The green trace is actually the inductor current, which I'm measuring with my current probe here, and this is a loop that I've put in order to be able to measure the inductor current. You will see here that there's a DC amount of current, right? So because that is the 0 amps point. So there's an average value here. The DC component is going to go through the resistor or my load. And then you've got this inductor ripple current on top of it. And as I said earlier on, the job of the capacitor is to reduce the amount of undershoot or voltage dip. I will demonstrate that in a minute. And reduce this ripple that will go through the capacitor and translate into a ripple voltage on our output. So let me change the trigger so that I can trigger on the current step. Set up that, and excellent. Okay, so by these are my load switches. And at the moment with this one switch here, I'm giving a 50% load to my power supply. I'm going to show you the output voltage of the power supply. Allow me to put the probe on. Okay, let me see. Okay, and I go to normal. And okay, at the moment, actually, if you have a look, you can see on the pink trace, this is the output voltage. This is on AC coupling, so that you only see the ripple. You already see the ripple, right? So the ripple current of the inductor goes through the capacitor and translates into ripple voltage. So this is one thing that we want to minimize. And we want to, when we give it a load step, we want to minimize the undershoot. So bear with me. There we go. You can clearly see it now. So the green trace is my inductor current. When it jumps from one value to a higher value is when I'm giving it a load step. I'm increasing the load. And you can see that at this point, the output voltage dips first and then it recovers, right? When it's recovering, it's my control loop. So the control loop has detected that the output voltage has fallen and it starts changing the duty of the power supply in order to make it deliver more power. If I expand the time base a little bit more, can I do this? No. Right? You can see that there is a dip right here. And the job of the capacitor is to minimize this dip here until the control loop gets a chance to react. Right? So we've got two jobs. One of them is to reduce this undershoot, this ripple, this undershoot, and the second job is to reduce the amount of voltage ripple.
Basically, the noise on power supply.
I'm sorry, please say again, Robert.
Basically, it's the noise on power supply.
Yes, it will be the switching noise on the output voltage of the power supply. You're absolutely
right. Okay, so what do we need to do to, like calculate this, or what is the next step? I don't know.
Yeah. Okay. So here's the situation, right? You've got three different requirements, effectively, and we need to meet them. So then that's why sometimes you get different equations. There are depending on what type of capacitor you're using, the calculations differ. So if you're using ceramics on your output, there's a different calculation for the ripple. And if you are using electrolytic, there is a different calculation for the ripple. And then on top of that, there is the voltage undershoot calculations, right? So you have two different requirements, right, for calculating the size of your capacitor. Three, if you consider that sometimes you have electrolytics and sometimes you have ceramics. So let me then show you what we do. We're going to first do the voltage dip requirement. Okay.
Okay.
So the allowable voltage dip on the output of the power supply is specified in the specifications, right? The time period that you allow it to dip before the control loop starts to kick in, right, is also often specified. If not, I will show you what is a good number to choose, right? So if you know how much dip you can have, there we go, delta V out dip, yeah, and you know how much time you have to recover, which we do from the specification, and you know the load step because that is part of the specification, then you can literally calculate the size of the capacitor for voltage dip requirements or undershoot requirements based on this school level equation. Q is equal to CV. We studied this at school. Q was equal to IT, and that equation is exactly the same as that. Look, this is IT here, that's your Q, this is your C, and that's your V, right? Okay, you know this one, you know this one, oops. You know this one, you know this one, you know this one, you can calculate this one. To give you a numerical example, if you know what is the crossover frequency of your power supply, You can use that equation. I've done other videos on that, or in our workshops, we talk about that a lot. If you don't know the crossover frequency, then don't worry. A good number, rule of thumb, around 5 switching periods that you allow for the voltage to drop to no more than 5%. So if you don't know your control loop requirements at this moment, it's not important. You go with these requirements. 5 switching periods and 5% dip is a good compromise. So let us say that I have a 5 volt 2 amp power supply with a switching frequency of 200 kilohertz. On a 5 volt rail, if I allow 5% dip or undershoot, that is 250 millivolts. So I know this. Yeah. And then let us say that we're going to give it a load step of 50%. That is a very common specification in industry. If I have a 2 amp power supply, a 50% step would be going from 1 amps to 2 amps. And that would be a load step of 1 amp. So there you go. That's the one that I have here. Finally, how long do I have until my control loop kicks in and will start to recover? We said a good rule of thumb, 5 switching cycles. Well, for a 200 kilohertz power supply, 1 switching cycle is 5 microseconds because it's 1 over the switching frequency. 5 switching cycles would be 25 microseconds. So 25 microseconds times 1 amp divided by 250 millivolts, 100 microfarads. It's the minimum amount of capacitance that I need. Of course, we allow a certain amount of margin, let's say 30 to 50% margin on top of that, and that will give you 30% on top of 100 microfarad will be 130 microfarad, but you can't buy one at 130 or it'll be very expensive because it's rare. 150 microfarad is a good number, or 2 times 68 microfarad. So that is the minimum that you're going to have in order to not violate your voltage undershoot requirements.
This looks so simple, actually. Like, wow.
Well, we can make it more complicated if you want, Rob.
No. I love it. I really like this because I think based on this example, everyone can calculate the value.
Well, yes, it's. I mean, in an ideal world, you want to know your control loop crossover frequency, right? But if you don't, 5 switching cycles is not a bad start.
Okay, I interrupted you, so you can continue.
No problem. Okay, so that's it. So let's hold this, right? And so okay, the minimum we need is around 150 microfarads, including the margin, right? Then that's the first calculation, right? So the second calculation would be for ripple requirements. And as I mentioned earlier, this calculation depends on whether you are using predominantly ceramic capacitors on the output of your power supply or predominantly electrolytic capacitors on the output of your power supply. And that is, again, a requirement of the application. For example, point of load power supply, the low voltage, high current power supplies that have to react very fast. Let's say you are feeding an FPGA or you're feeding a big microprocessor, are typically ceramics, right? And therefore, you do the calculations for the ripple based on the ceramic equations. And I'm going to show you one in a minute. Mass majority of other power supplies, the very, very common choice is electrolytics, and the calculation for electrolytics is different. So let us first assume that we are going to use ceramic capacitors and do a calculation. I will show you the ripple then, and then we will do it again a third time for if you are using electrolytics. Okay, so if Cout is predominantly ceramic or polymer capacitors are also becoming very popular, then the ESR of the capacitor is very, very low. ESR stands for equivalent series resistance, and our capacitor, the textbook capacitor, has 0 equivalent series resistance, but this is a parasitic that exists. On ceramics and polymer, it's very, very low, so at least for ripple calculations, we usually ignore it. We say, you know what, all of the ripple is because of the amount of capacitance that we have, and we set ESR to 0. For electrolytic is the other way around. So we're gonna, and that's my third calculation. So we talk about that a little bit later. So we are giving a ceramic example for now, let's say a small a power supply feeding an FPGA or whatever. So I assume that the ESR is 0, and then I calculate the capacitance as a result of ripple, based on this equation here. Now, this is for a buck converter. You can find these equations with 5-minute search on the internet or any standard textbook. An excellent textbook that lists pretty much everything is the fantastic book by Mr. Maniktala. I have put the reference down here. And for a buck, the output capacitance has to be bigger than this equation. This up here is the peak-to-peak ripple current that is specified, so you know this, right? Switching frequency, you know, and the amount of output ripple that you can allow is also from the specification. If you don't know it, or if it's not specified, then again, 1% of the output voltage is a good number. So how much capacitance do I need so that my ripple falls below this desired level, right? Again, I know this one, I know this one, I know this one, I know 8. I can calculate my C out, and that's my second calculation. Then I compare that with the calculation that we did just a few minutes ago, 150 microfarad, and whichever is bigger is my worst case. Right?
That's what I wanted to ask. So basically, this doesn't mean you need 2 different capacitors. We are talking about one capacitor. We are just trying to find out what is the value, and which one is the bigger one. That's the one what we will use.
Yes, you need to pick one that doesn't violate either of these 2 requirements.
Yeah.
And that's why we calculate it twice, right? And we see which capacitor, what size capacitor meets both of our requirements.
Yeah.
Okay, so I'm going to give a numerical example now. Let us say that we have got a 5 volt output voltage. Let us say that we're going to allow 1% ripple on the output voltage, and that gives me 50 millivolts. And then my peak-to-peak inductor current, I know because actually I have to calculate that first. Again, in our workshops and in the videos, we show that you have to calculate the inductor first, and that is based on the ripple current. So this value is known from your specification. Switching frequency is known from your specification.
I have a question. I'm sorry for interrupting.
Yes.
But we can also measure this peak-to-peak current. That's what was on the
scope.
Yes,
you can. That was the green trace that I showed on the oscilloscope.
Okay, perfect. You can continue.
Okay. For a buck converter, then this was my equation. I know this, I know this, I know this, I know this. I can calculate it. And in my case, it comes out to be 10 microfarads. Okay. That is for ripple requirements. But remember, we said we needed 150 microfarads for the dip requirements. So which one do we pick? The 150 microfarad, because obviously that is my worst case. Yeah. And then remember that we're using ceramic capacitors now. We need to allow some margin for the DC bias loss, because the capacitance falls quite a lot with ceramic capacitors of high value. If you put a lot of DC voltage across them, allow 100% margin. So we calculated 10 microfarads. If you need to allow margin, then that'll be 20 microfarads, right? And then on top of it, buy a voltage rating that is much higher than what you have, what the actual stress is. So if the stress on this capacitor is 5 volts, try to buy a 10 volt or a 16 volt capacitor to minimize the amount of the DC bias loss. But I'm going to show you an example a little bit later anyway. So I'm going to show you the ripple voltage now. Okay.
Okay, I would like to add to these capacitors before you show it. So if someone would like to understand a little bit more what we just mentioned, it's very easy to do.
Yes.
If they find, people can find specific capacitor, and then there are some parameters. They can see there are few graphs, and very quickly people will notice that if there is DC voltage on capacitor, capacitance drops very quickly. Yes. That's exactly what you mentioned here. That's why we need the 100%. And also parameters of capacitors with higher voltage, what we need, are better than if we would go for the capacitor, which is exactly for the voltage what we need. That's why we would like to use capacitor for higher voltage, correct?
Yes. So you have to allow some margin anyway, right? Because of safety reasons. However, the capacitance of ceramic capacitors falls as you increase the voltage across them, DC voltage across them. So that is why if you calculate 100 microfarad and then you put too much DC voltage across it, this value falls. So if you put more margin for yourself, then this value will not fall as much.
Yeah.
So you end up closer to what you calculated.
Yes,
with the amount of
exactly.
capacitance that you have.
Okay, we can continue.
Okay, so let me then go and show you the ripple then. Oh, I need to bring the
Scope,
instrument back, don't I? Right.
So now we are going to have a look at ceramic capacitor, correct?
Yes. Yes. Okay. So I'm going to now swap the converters, right? And I'm going to use one that is over here. This one is a constant on-time converter, and the output capacitors are all ceramic. So we're going to have a look at the ripple based on all ceramic caps, right? So allow me to switch things over. I need this. I need my gate. And I need this. Okay.
So the yellow is again the gate.
Yes, yellow is the gate. I'm just going to trigger on that. Set up channel 1. There we go. That is my gate. And the pink trace is the output voltage, right? First, let me put it on DC coupling, and you see how the actual output voltage works, right? So there you go. That is my output voltage. You see when the scale is up and this is reading 5 volts. It's absolutely beautiful. You can barely see anything, right? And then I'm going to zoom into it. So first I'm going to put it on AC coupling so that I take out the DC component, and then I can zoom in. So I'm going to then set that to AC coupling. And then if I zoom in, you're going to see the ripple. There we go. That is beautiful. Look at that. That is the ripple voltage. You can see that is sort of pseudo sinusoidal. And you can see these switching spikes, right? This is because of the switching noise. Let's see if I can make it any less. Not really, right? And the total ripple that you have on this particular converter, cursor, channel 2 is there you go, 6 millivolts I have on this, which is nothing on a 5-volt power supply, right? Okay, now bear in mind the shape of this ripple, because I will show you what it will look like if I have electrolytics instead. This converter is identical to this one, and this one has got an electrolytic output capacitor, and this one's got ceramic output capacitor. So we're going to talk about electrolytic in a minute. Okay.
Okay. So basically,
All right.
the value of the capacitor on this power supply for this load is fine, because the noise, the ripple is very low.
In this particular one, yes. I mean, it has been designed to meet a certain specification, right?
Yeah. Okay. Perfect.
So yeah, that's it.
Okay. So what is difference between the ripple on ceramic capacitor and the electrolytic? I'm curious.
Oh, that's a great question. So let me save this and let me compare them. Yeah.
Okay.
Okay. So I'm gonna put that down here. That is the ripple due to the ceramic capacitor. Can I make it any better? I'm not sure. Oh, I nearly got it. Just bear with me. There we go. So I'm just going to save this. reference to save.
Yeah, we can actually see how the capacitor is discharging and charging, discharging and charging.
Yes, that's exactly what is happening. And remember that the inductor current was a ramp, right? So turn that off. So you can see that it's not exactly sinusoidal. Can you see it's kind of a ramp up here and is ramping down?
Yeah.
Right? And that is because the inductor current is a perfect ramp and it's being integrated by the capacitor, right? If you remember again from university physics and engineering lessons, right? The ripple voltage across the capacitor was 1 over C integral of I dt. So the capacitor is integrating the current with respect to time. The current is a ramp. Therefore, the integral of that would be a parabola going up. And you can kind of see it here, right? It's a parabola going up and it's a parabola coming down, but to us looks like a sinusoid. And that's the ripple voltage for a ceramic capacitor.
Okay.
Now, for an electrolytic capacitor, the ESR of the capacitor is very, very big. So the ripple that appears across the electrolytic capacitor is predominantly due to resistance. And of course, if you put a triangular current into a resistor through a resistor, you get a triangular voltage out, right? So for electrolytic, I expect the ripple to be triangular rather than this pseudo sinusoid. You see what I mean? Okay, so let me show you. So this one is identical to that one, and the only difference is that this has got an electrolytic on it. And we're going to look at the ripple across this electrolytic.
Okay.
Right? So just allow me a couple of minutes to swap my probes and power around.
I'm curious. So this is basically why we have to use two different calculations for between ceramic and electrolytic, because they, even on these waveforms, we can see they behave differently.
Yes. And it's a bit confusing because when you're looking for equations or in textbooks and so on, you kind of get 3 different equations and you don't know which one is right. But the answer is all 3 of them are right. One of them is for dip, one of them is for ripple if you're using capacitors, ceramics, and another one is for ripple if you're using electrolytics. Yeah. Okay. So now swap this over to this one. Turn that on. Excellent. Okay. So this is a constant on-time power supply, right? Identical to this one. The difference is that this one has got electrolytic. So let's have a look at the ripple on this one.
I'm curious.
Look at that. Can I make this a better measurement? Bear with me. I'm going to try and find a better place to measure it because it's very, very noisy there. So there we go. That's my switching frequency. Oh, look at that. First of all, it's huge compared to the ceramic. All right.
It's same scale.
Same everything. All right. Switching frequency the same, right? The amount of capacitance actually, I believe, is the same, right? It might be a little bit different, but not too much. But the ripple, I need to zoom in. The ripple was this big, right, compared to ceramic. I'll measure it in a minute. We had 6 millivolts on the ceramic, right? Okay, look at that. And the really interesting part is that the ripple voltage across the capacitor is not a sinusoid or a pseudosine. It's a triangular wave. Is identical to the ripple across the inductor in terms of current. Right?
This is interesting.
So what is creating this ripple? A resistor or a capacitor? We know that the current is triangular and the ripple voltage is also triangular. So that's Ohm's law, right? It's clearly the resistor, the ESR of the capacitor is the bit that is contributing the most to the ripple. Therefore, when we use an electrolytic capacitor, we base our calculations on the amount of ESR that it has. Yeah.
So
And it's
what
much,
is
much
the
bigger, but nearly identical, right? I'm not sure of the exact specification, right? But they're not too far off. Let me go to my cursor.
yeah, and measure? I'm curious.
And let me measure it. Right. So I need to go to channel 2, right? Source is channel 2. There you go. The ceramic one was around 6. And the electrolytic one is 130. Okay? And the shape is a resistor, right? This is not the ripple is not because of the capacitance. The ripple on this one is because of the resistance. Okay, so now that we know this, we can go and calculate it. Okay, so let me turn that off. Okay. So as I mentioned earlier then, and as we saw from the measurement, the ripple, if the output capacitance is predominantly electrolytic, is as a result of resistance. And that is why you got a triangular ripple as opposed to a pseudosine, right? And then if it's a resistor, then it's just Ohm's law, right? This is, there you go. This is V is equal to IR. This is your I, this is your R, and this is the ripple. Again, the amount of ripple is specified. The amount of current ripple is specified. You can calculate the maximum ESR that the capacitor can have before it violates the ripple requirement. Right? And then you go and find a capacitor with the value less than that. Okay. So
Okay, I would like to point out. So basically, in this case, we don't really care much about the capacitance because this ESR is the dominant element which is making these ripples. That's why we only.
yes, absolutely.
Yeah.
Absolutely. So actually, we don't care about the capacitance at all in this particular case because it's the resistance that is generating the ripple. But we cannot violate the dip requirements, remember? So we said that you must have a capacitance bigger than 150 microfarads earlier on.
Yeah.
So as long as we have a capacitance of bigger than 150 microfarads with the resistance smaller than an ESR of smaller than a value that we calculate from here, that's all we need to calculate.
Perfect.
Okay. So again, I'm going to give an example, right? Let us say that again, I'm going to allow 1% ripple on the output voltage. 5-volt power supply, that's 50 millivolts, right? Again, let's say I have 800 milliamps of ripple on my current. These are all part of my specification. This is Ohm's law, right? V is equal to IR. 50 millivolts divided by 800 milliamps, 63 milliohms is the maximum amount of ESR that my capacitor can have before it violates the ripple requirements. And 150 microfarads was the one that I was going to buy to make sure that I don't violate the undershoot requirements, right?
I would like to point out here, I'm sorry for interrupting, because I'm sure everyone who ever designed any switching power supply, they read somewhere about this ESR, keeping ESR low. So here we have the exact example why we would like to use capacitors with low ESR, because otherwise we can have very big ripple if the ESR is not low enough.
Yes. But again, as with everything else in engineering, you get one advantage and you get 5 headaches, right? So having a little bit of ESR is not a bad thing when you come to design your control loop because it damps everything and it makes control loop design easier. Right? So it's a compromise like everything else that we do.
Okay, what do you have next? I interrupted you again. I'm sorry.
No problem. Okay, so then I want to go and buy my capacitor now, right? So I've got the capacitance, I've got my resistance. So I still need a couple of other numbers, and then I can go and buy one. And I'm gonna show that, right? As to how we're gonna buy one. few things we need to consider: the amount of tolerance that the capacitors have. For electrolytics is typically plus minus 20%, right? For ceramics high value, they say 10%, 20%, but remember again, there's that DC bias loss, so we allow a margin of 100%, so we double it, right? Then voltage rating. If you're using electrolytics, 20 to 30% margin. So if you in this case, we have got a 5 volt power supply, 20-30% on top of that gives you a very strange number. You can't buy a 7.6, 8 point whatever capacitor. You go one level up to 10 volts, 16 volts, right? With a ceramic, the same, but again, allow 100% margin, double it. So 5 volt power supply, that's the stress on the capacitor. You double it, 10 volts, 16 volts is a good number, right? And then the ripple current rating of the capacitor is what the manufacturer specifies in terms of RMS value. So when you go to the manufacturer in order to find a capacitor, and you're going to check how much ripple current it can tolerate, that is the RMS value. But the number that we have is the peak-to-peak value so far. We use the peak-to-peak value in order to calculate the inductor, and then later on we used it to calculate the capacitor. So we need to convert that into RMS before we're going to go and buy one. Otherwise, we'll over-engineering it. So the example that I gave was that the peak-to-peak current was 800 milliamps. It's a triangular wave. So to convert a triangular peak-to-peak to RMS, you divide it by 2 times the square root of 3, right? So I need an RMS ripple current value of my capacitor that is more than 230 milliamps. You again allow 20-30% margin. You buy one for 275 or more, right? And that's all you need in order to go and buy your capacitor. So I think what we're going to do next is we're going to go and find one. Yeah. Okay. So
we know all the values. Now we are going to find.
We know everything, right? We know everything to go and get one now. So there we go. For convenience, I've put it on this slide. We need 150 microfarads to meet the dip requirements. We need an ESR of 63 milliohms or less to meet the ripple requirements. This is for a power supply with electrolytic capacitors on the output. Then we need a voltage rating of 5 volts plus 30%, which is around 8 volts. But it's hard to find an 8-volt one. So we go one up to 10 or 16 volts. Yeah. And we calculated that the RMS value of the ripple current was 230 milliamps. You add another 20-30% margin to be safe, 275 milliamps. That's all I need to go and calculate my capacitor. Okay, so the website that I use in order to get my capacitors is the Red Expert from Worth Electronics. Now, just to say that I don't get paid by Worth Electronics. I just really love this tool because it's just so quick and easy to narrow down my capacitors and get to the one that I want. So there we go. We go to capacitors, then aluminium electrolytic capacitors, and it gives me a grand total of around 2,000 choices, right? So then let us narrow down with the requirements that we have. So starting from here, first of all, we said that we're going to have aluminium electrolytic, right? So I'm going to use this filter on Red Expert to narrow it down, and it goes from 1,990 to 1,600, right? Okay, then we said that the minimum amount of capacitance had to be bigger than 150 microfarad. So let me narrow down my choices and only look for from 150 microfarads to 330 microfarads. Right? And it goes down to 314. We started with 2,000 choices, and now with 300 choices. Then we said that the voltage stress was 5 volts. We allowed 30% margin, which came to 8 volts. And then we said, you can't find 8-volt ones. Let's get one between 10 or 16. So again, I used the tool to narrow it down. And if I go from 10 or 16, it goes down to 82 of them. Yeah.
Okay.
And then if you remember, we said that the ripple current rating had to be, was it 275, I think? It was 275. Yeah, okay. So including my margin, it was going to be 275, right? So let me go to specified maximum ripple current, and I say that I want it to be bigger than 275 milliamps, right? It goes down to 56, yeah?
So do you select
Finally, we
some kind
said,
of frequency there, or?
yes. So the ripple current rating goes up with frequency, right? You're very observant, and you notice this graph here.
Yeah.
Yes. So it goes up with frequency, right? And therefore, this tool provides you with a multiplier, right? To allow you to calculate it exactly at the correct frequency. And of course, our frequency is 200 kilohertz, right? So I have already set it to
But it's
200
100
kilohertz up here.
kilohertz.
I'm sorry?
It's set to 100 kilohertz, no?
No. Okay, it's specified 2 times, right? There's one specified here, right? If I, it's really cool, this tool. Look, if I change the frequency, my switching frequency, it recalculates it and displays it there. Right? Anyway, so.
Oh, this is interesting.
Oh, it's a great tool. Again, I stress, I don't get paid. I just love these by worth. I just love the tool. Okay, so then finally, let me, okay, 275 I've done, right? And then if you remember, we said that ESR had to be less than 63 milliohms, right?
Okay.
Again, here's ESR versus the frequency. For ripple calculation, I need the ESR at 200 kilohertz because even though it's a resistance, it changes a little bit with frequency, right? Can you see? Okay, so my ripple is at 200 kilohertz. I look at the value at 200 kilohertz. As soon as I move this slider, it gives me the ESR at 200 kilohertz, yeah? And it has to be less than 63 milliohms or I violate my ripple requirements.
So
Whoa, there you go.
items.
I have 2. I started with 2,000. I have 2. Buy one of these 2, and both of these will not violate all the requirements that you have, right? And the difference between them is actually the lifetime. Look, if you're making a product that needs to live for a long time, this one. If there's one that doesn't have to have a very long mean time between failures, and you need a cheaper one, that one. We're done. So that's my capacitor.
I love this. Can we have a look also on ceramic capacitor? Because I would like to show the graph, especially the DC bias is, I think, very important so people understand why we have to use 100% tolerance or
yeah, we can do
100% safe margin.
Yeah. So let me go back to beginning page because it's on a different page, I think. There we go. And then capacitors, and then we go to ceramic capacitors, right? Okay.
Oh, so, I can see DC bias.
Versus DC bias, right? And this is normal. All capacitors, all big microfarad ceramics are like this. Now, if you if I remember, it was 10 microfarad, wasn't it? What we calculated? Let's do 10 microfarad. And the higher the microfarad, the worse this is, right? So 10, it's this 10 nano. Let's do 10 micro. Look at that. All right. Okay. So this is 100 volts. Let's pick a 50 volts one.
Okay.
Right. By the way, if you pick more than one, right, it plots them over each other. Can you see? So you can compare them. Oh, this one is really bad. What is this one?
16 volts.
Yeah. Because look, this is 100 volts one. The red trace is 100 volts. As you go up from 0 volts to 100 volts, 10 microfarads becomes 1.65 microfarad. If you DC bias it by 100 volts, that's the rated voltage. So at 100 volts, you don't have 10 microfarad. At 100 volts, you have around 2. Yeah? And that's why we say put yourself a massive margin. The green one you see here is a 16 volt one. It's that one there. Yeah?
It goes rapidly down.
It goes to nothing, right? And that's why I'm saying put big margin or parallel lots of them. Instead of buying 10 microfarad one, buy 10, instead of buying 10 microfarad one, buy 10 1 microfarad ones. Because 1 microfarad does not have as big a problem as this.
Also,
but again,
the voltage.
The tool shows it to you. Yeah?
Also the voltage, we can very nicely see we can rather buy capacitor for 50 volts than for 16
Yes.
volts because the parameters
Yes.
are much better.
Yes.
This was really cool. Do you have anything else in your presentation?
That's it, actually. We showed how you select the electrolytic capacitor based on the ESR. Then we kind of went off track a little bit and we talked about ceramics and why you have to put an extra margin on the voltage because of DC bias loss. So really, you've seen all of these equations. What we have done next is we have put all of them into our software, which basically calculates all of this for you. There's a lot of calculations that you have to do, conversion between peak-to-peak and RMS and ESR, calculating the ripple based on ESR, the equation for the ripple based on what topology you have, and so on. So what I've done is we've created a software called Breacher WDS that designs the entire power supply, including control loop, and it does all of these calculations inside. So we now know how to do it by hand, but then after we know how to do it by hand, we just go and use the software. And of course, everybody who comes to our workshops gets a license for this software as part of the workshop fees.
So the software is not free, but if
The
someone would
software
like,
is not free.
if someone would like to
There's an
buy,
evaluation version that you can download, but the software itself is not free. If you attend one of our workshops, you get the software license as part of your workshop fees.
okay. So basically, if someone would like to calculate it manually, now everyone understands how they can do it. If they don't have time, they can use your software, and software will tell you what kind of parameters for capacitors you need to use, correct?
Yep, that's it.
Okay, so what do you do actually? You mentioned you do trainings?
Yes. So I run a company called Breacher Digital. We have been going since 2008, and we run hands-on engineering workshops based on we teach power supply design and EMC.
Oh, that's
EMC
why you
filter
know so
design.
much about power supplies.
Well, I've been doing it a long time, Robert. Okay. And we run these workshops in Montreal, where I live, and also in Munich, where I also seem to live because I'm there all the time. They're both very, very cool cities. The next ones, we run them all throughout the year. So you just go on our website and see when is the next workshop closest.
Do you have a website?
We also are going to start running online workshops very soon.
We can open your website. I'm just curious.
Yeah, sure. So this is the website. These are the workshops. And you can see that right now, at the time that we're recording this, we are running one in Austin, two in Montreal, several in Munich. And the hands-on workshops is based on the boards that you saw. So engineers who come actually really get to play with the power supply, make the measurements, and actually calculate things. And as I said, they will get the software, which will do all the donkey work. So after they learn how you do it by hand, then we just use the software to help us do the calculations quicker. And as I said, we do analog power supply design, digital power supply design, EMC filter design. I've got online workshops, and EMC debug is also coming soon.
Thank you so much, Ali, for this. It was super cool because I think it's going to help many people because in many data sheets, actually, you can read choose the right output capacitor, but very often they don't exactly explain how to choose the right output capacitor. So I really hope this video, what we just created, is going to help many people. Thank you, Ali.
Thank you very much, Robert.
That's all for this video. I hope it was helpful. If you would like to learn more about electronics and board design, check out our online courses. You will find everything important there, from basic board design up to advanced board design and high-speed PCB layout. We have courses in Altium, Cadence, KeyCut, and also courses covering many different topics, for example, FPGA, EMC measurements, and so on. Visit our website at fedevel.com. That's all for this video. Thank you very much for watching, and don't forget to leave your comments. See you in the next video. Bye.